Hi everyone, we're continuing with sections 5.4 and 5.5 on these additional trig identities. But first, I want to take you back to section 4.7 and this creature that we, in a way, simplified algebraically last time, or that time. Cotangent of inverse cosine of x over 3. This was an expression that mixed a basic trig function and an inverse trig function. So here, we had this mixture of functions, and we couldn't really apply the inverse properties. If this were cosine, maybe we could. But in this kind of a mix here, it helped to do a right triangle solution. Something like this. Or use related Pythagorean identities. Now, we're going to consider an expression like this. We're going to write sine of 2 arc cosine of x. The 2 here is the irritant. We're going to write this as an equivalent algebraic expression in x. Again, that's an expression we might have seen back in chapters 0, 1, or 2. In section 4.7, for example, it turned out that this expression here was equivalent to this algebraic expression down here, x over root 9 minus x squared. That's algebraic. Think of the quadratic formula and its structure. But how can we rewrite this? The 2 there is irritating. Well, let's first apply a substitution. That would help. In my solution here, I don't apply it as aggressively as I probably should have, but I'll apply it aggressively. Let's substitute. U equals arc cosine or inverse cosine of x. So basically, we're dealing with sine of 2u. Sine of 2u. So you think of what identity? Well, it might be hard to read it like that. This here. The double angle identity for sine. Sine of 2u is 2 sine of u cosine of u. In fact, I would probably put that as part of my actual work. So this is sine of 2u. And sine of 2u equals this stuff over here. Okay, now, and you don't even have to sub back. We can kind of keep this in u for now, all right? But now we got to figure out, so what are sine of u and cosine of u? So if we can get expressions for sine of u and cosine of u in terms of x, remember our ultimate goal is to get an expression, an algebraic expression in x. If we can express sine of u and cosine of u in terms of x, we're really there. We're really done. Well, right off the bat, u equals arc cosine of x. Or another way of looking at it, I'll turn it around and use the inverse cosine notation. Inverse cosine of x equals u. Inverse cosine of x equals u. Well, if inverse cosine of x equals u, then that means that what is true? Cosine of what is what? If inverse cosine of x is u, then cosine of u is x. Remember, when we go from a statement to its inverse version, the inverse statement, we're switching the inputs and the outputs. It's similar to what we did in section 4.7. If theta is inverse cosine of x over 3, or if this equals theta, then cosine of theta is x over 3. It was very similar to that. So cosine of u is x. Hey, wait a minute. Cosine of u is x. I know exactly what this guy is. This guy is just x. So that part comes through in a fairly straightforward fashion from here if you understand this inverting process, writing the corresponding inverse statement. It's kind of like going from a log form to an exponential form, a zigzag. Okay, anyway, cosine of u is x. So this here is x. This ugly expression, cosine of u is x. You may not want to write all this out. This looks pretty intimidating. Let's look at this. 2 sine of u cosine of u. We know cosine of u is now x. The question now becomes, what is sine of u? What is sine of u? Well, we can either use a Pythagorean identity, or it might be friendlier to use a right triangle. Remember, cosine of u is x. Another way to look at it, cosine of u is x over 1. So katoa. Cosine is adjacent over hypotenuse. So a natural model for this statement would look like this. Cosine of u, this angle here, is equal to adjacent over hypotenuse. X over 1 is x. And then how do we get this missing side length over here in terms of x? We use the Pythagorean theorem. So we could call this b, for example. Do I do the work? No, I don't do the work, but you can work this out. I'll write this in blue. Okay, so we have x squared plus b squared, this guy we want, x squared plus b squared equals 1 squared, or just 1, right? 1 squared is 1. Don't engage in wishful thinking. Don't put the b squared alone on one side. He's buried in there. But you want to solve this for b, and it turns out that you get b equals plus or minus the square root of 1 minus x squared. And it turns out that we don't need the plus minus symbol. It works out, okay, even if u is not acute. You can remove the plus minus symbol. You can remove the plus minus symbol. It works out. You can look at various cases, but it does work out that you don't need the plus minus. So b is simply root 1 minus x squared. And that's important because now we can find out what sine of u is. Remember, that was the piece that was in a way not missing, but we needed to express this in terms of x. We had to express sine of u in terms of x. Okay, so what is that? So katoa sine of u equals, from u, opposite over hypotenuse. So that's going to be b over 1. What was b? It was this guy, root 1 minus x squared. It's moved over here. 1 minus x squared over 1. 1 minus x squared over 1. Okay, root 1 minus x squared. So that goes into here. So this thing in here is going to be the quantity, or just the square root of 1 minus x squared. That goes in for sine of u. We're substituting that in. So we get 2 times that times that. We normally bring the polynomial pieces out in front to the left. So we end up with 2, we move the x over here normally, and then times the square root of 1 minus x squared. And that's algebraic. And in some ways, that's a lot nicer than the original expression over here. And in calculus 2, maybe you have to re-express this in this fashion. This might be easier to manipulate. 2x times the square root of 1 minus x squared. That's algebraic. In fact, we could even go to Desmos. All right, let's go to Desmos. Here's sine of, what was it now? It was sine of 2 arc cosine of x. Sine of 2 arc cosine of x. All right. Domain looks to be from -1 to 1. Range looks to be from -1 to 1. Okay. And I claim that this is equivalent to 2x times the square root of 1 minus x squared. Hey, look at that. I'm just recoloring the graph. Not a proof, but I'm pretty convinced these are equivalent. Not bad, huh? And this looks a lot friendlier than that in some ways. Well, there is a certain elegance to this in some ways, but this is algebraic. And these are equivalent expressions. They even have the same domain. From -1 to 1, you might be able to see that. All right. Now, sometimes in placement exams, you might see something like this. Cosine of these guys here. And remember that these inverse tangent values, we often associate them with angles. So you might call arctangent of 1 u, where u is like an angle, and arccosine of x like v, where v is like an angle. And then you can use this identity here, right? Cosine of u plus v. You use this identity, and it turns out that you can use procedures similar to what we just discussed. You can try this out. All right. Next up, we're going to look at some PRIs, which are used all the time in calculus, especially Calc 2, Math 151. Next time.